For the do now, there's just actually one question. So we have this equilibrium reaction, and we have a Kc value. It says at a certain point in time, a 1 liter rigid reaction vessel contains 1.5 moles of PCl3. So here's what I'm going to do. I'm going to kind of just label everything. So 1.5 moles of PCl3, 1 mole of Cl2, and 2.5 moles, that's 2.5 moles of PCl5. Is the system at equilibrium? How will the pressure change if it's not at equilibrium? So I kind of gave a hint here. I said first solve for Q. We're going to talk more about Q versus K today. The importance of Q versus K. Remember that K, right? So in this case it's Kc. This is the equilibrium constant at equilibrium. So if this reaction is at equilibrium and we do products over reactants, our value should be 6.5. But what if we're not at equilibrium, or we don't know if we're at equilibrium? This just says at a certain point in time. So if it's at a certain point in time, we don't know if we're at equilibrium or not. That's when we use Q. And so what I'm going to do over here is I'm going to solve for Q. Now because it's Kc, I'm technically solving for Qc. Now what's the difference between solving for them? Nothing. Absolutely nothing. Solving for Q and K is the exact same. Products over reactants, you do not include solids and liquids. The only difference is that instead of writing K out front, we're writing Q because we don't know where we're at in the reaction. So if I do products, which is PCl5 over reactants, PCl3 times Cl2, I can solve for Q. I added brackets because it's QC. That's concentration, that's moles over liters. Well, here's moles. It's in a 1 liter container, so it's also 1.5 molar, 1.0 molar, 2.5 molar. Because it's moles over liters, it's a 1 liter container. So if I solve for QC, I'm going to have 2.5, that's PCl5's concentration, divided by 1.5 times 1. So really it's 2.5 divided by 1.5. Should I be able to do it in my head? Probably. Can't I this morning? Nope. So Q, right, QC, is 1.67. So the first question, is the system at equilibrium? You compare Q and K. If Q is equal to K, it is at equilibrium. Well, first, is Q equal to K? No. 1.67 is not 6.5. So is it at equilibrium? No. Right? Q is not equal to K. So then it says, how will the measured pressure change if it's not at equilibrium? So I'm going to talk through this right now, but then we will go back and we will talk through it again when we look at Q versus K. So first, if you don't know if it's at equilibrium, or now we've determined that it's not at equilibrium, I'm going to start by talking about how Q is related to K. So I'm going to start by saying Q is less than K. So Q, my value of Q, is less than my value of K. I'm going to show you a way, like a visual, helps me think about it. But if Q is less than K, right, this ratio is not what it should be to equal 6.5. So you need to think about, if I want to increase the value of Q, because I want Q to equal to K. The goal is to get Q equal to K. The goal is to get to equilibrium. Well, if I want to make the value of Q larger, if I add more products, that will make my value of Q larger. Right? If I add more products, that will make my value of Q larger. So Q is less than K. So I'll say, so the reaction needs more products to achieve, achieve, I can't spell achieve ever, so, right, Q is less than K, so the reaction needs more products to achieve equilibrium. Now, this is specifically asking about pressure. So what we have to do is we have to look at the reaction itself. It's going from 2 moles of gas, so if we need more products, our reactants are going to combine and be used up to form more products. Now, are they all going to be used up? No. But some of them will react to produce more products. So think about it. If you're going from 2 moles of gas, right, 2 moles of gas colliding, down to 1 mole of gas, your pressure is going to decrease. So I'm going to say pressure will decrease as reactants, and I'll say 2 moles of gas form products, which is 1 mole of gas. So the measured pressure will decrease because the reactants, right, 2 moles of gas, are combining to form just 1 mole of gas. So we're going from more collisions to less collisions. So that's it for the do now. Again, we will talk more about Q versus K. We have one example to do before Q versus K. So if you have questions on this right now, kind of write them off to the side. So that way when we go over Q versus K, right, that's when we'll answer those questions. So for today, you will want your notes. You will want a calculator. Should be it. Notes and calculator, I believe. We have 3 examples based on last night's video. And then we actually are going to do 3 particle diagram examples. The 3 particle diagram examples, one of them will be looking at Q versus K, but the other 2 are just going to kind of be looking at equilibrium in general. So this is right out of the notes. I just took this information in the notes and I just put it onto a slide. So calculating equilibrium concentrations, this information in the notes is on page 7. So on page 7 of the notes, it says calculating equilibrium concentrations. So we have looked at ICE tables. We looked at calculating using ICE tables when we had initial and an equilibrium amount. We could figure out the change, and we could plug in and we could solve for the equilibrium constant. Well, calculating equilibrium concentrations is the same math. It's the same setup in an ICE table, initial, change, and equilibrium. But when we want to calculate the concentrations at equilibrium, we usually don't have a number for the change row because we don't have any information about equilibrium concentrations. And so the difference between what we looked at before and what we're going to look at today is that if we don't know the change, we're going to use the variable x. So we're going to assume that it changes by x molar or x ATM. And we're still going to use the stoichiometry, but now we're going to have a variable. And so you might have to use the quadratic on some of the practice or on mastering. You will not need the quadratic on tests and quizzes. If you do need the quadratic on mastering, one of the practice problems today has a quadratic formula question. Just use an online quadratic formula calculator. If you Google quadratic formula calculator, you can type in your value of A, your value of B, and your value of C. So you will not need to do that, though, for a test or for a quiz. I'll show you what a test question or a quiz question would look like with the example that we're going to do, because sometimes you have perfect squares. So when you have perfect squares, you can take the square root of both. So what we're going to do is we're just going to jump into an example. So we're going to actually flip back to example 4. So if you remember when we were doing all of the examples at the beginning of equilibrium, we skipped example 4. So we're going to flip back to it now. This is on page 12. Bottom of page, nope, not 12, 11. Bottom of page 11. I just can't count. All right, so example 4 is on the bottom of page 11. Now here's what I'm going to recommend. I'm going to recommend that you kind of split the question like this, not evenly. Because what we're going to do is we're going to answer the conceptual part over here on the left, and then that's going to leave us lots of space over here on the right to do math. So I recommend kind of splitting it off center so that here we have space to answer the conceptual question, and then we can also look at the math. So for this example, it says consider this reaction below, and they give us the Kp value. When you are given a Kp value, underline it, circle it, box it, something, so that you know that you can go back and you can reference the K value if needed. Now I'm just going to, before I read anything else, I'm just going to kind of write some information about what I know if Kp is a small number. So Kp is 1 times 10 to the negative 5th. And that's a very small value. So a very small K. So if K is less than 1, if this value is less than 1 times 10 to the negative 5th, K is less than 1, if it's very small, reactants are favored. So I like writing information about equilibrium constants if we're given them, because it might help us with the question. So Kp is 1 times 10 to the negative 5th. It says suppose we start with the pressure of Br2 being 1 atmosphere, the pressure of Cl2 being 1 atmosphere. And the system is allowed to come to equilibrium. So it said that we're starting with these amounts. So I'm just going to label these initial, just in case I need them. Then the question itself says, without doing any math. Okay, no math. I'll go ahead and leave my calculator down. So without doing any math, what can we predict about the relative partial pressures of Br2, Cl2, and BrCl at equilibrium? So if you want to look at how things exist at equilibrium, look at your value of K. Your value of K tells you what you have at equilibrium, right? What you have more of, what you have less of. So we actually already wrote some information that will help us out. Reactants are going to be favored. This is just asking about relative partial pressures. It's not asking for values. It just wants to know you're going to have more of this, less of this. So here's what I'll say for our conceptual part. Because Kp is very small, reactants are favored. So I'll say the pressure of Br2 and pressure of Cl2 will be greater than the pressure of BrCl. So because Kp is so small, the reactants are favored at equilibrium. We expect the pressure of Br2 and the pressure of Cl2 to be greater than BrCl. And I could even go a step further and say the pressure of BrCl will be very small. Because if K is so small and there are mostly reactants, we wouldn't expect there to be a very large pressure of the products. So there's the without doing any math portion of the question. Just conceptual. If you are looking for information at equilibrium, look at your K. Your K tells you what is favored, what you have more of, what you have less of. So, now let's do math. I know it says without doing any math, but now I'm skipping that part, and over here I'm going to do math. So now what I actually want us to do is I want us to calculate what the pressures will actually be at equilibrium. So this is going to practice with our ice tables. So if we want to actually calculate, I'll kind of write this right here. If we want to calculate, I'm just going to use brackets for concentration to save myself space. So if we want to calculate equilibrium concentrations, we can use an ice table. If we want to calculate equilibrium concentrations, we can use an ice table. So here's what I'm going to do. I'm going to rewrite my equation, right? Our steps for an ice table. I'm going to rewrite the equation here. Now I'm going to go ahead and set up an ice table. The process of the ice table is no different than what we looked at before. Initial. Well, they gave us initial amounts here. We start with the pressure of Br2 and the pressure of Cl2 being 1 atm. Well, remember, the only two units that can go into ice is either molarity or atm. So here's 1 atm and 1 atm. It said nothing about pressure of BrCl initially, so it's 0. Now, we have nothing else. We have no other concentrations, no other pressures, amounts, anything. So we're going to use X. Now, the change row is still based on stoic. I'll worry about the pluses and minuses in a second. But Br2 and Cl2 have exponents of 1. Well, not exponent, coefficients of 1. BrCl has a coefficient of 2. There's twice as much BrCl. So its change will be 2x. So the pressure increase of BrCl is going to be twice as much as Br2 and Cl2 because its coefficient is twice as much. Now, if you start with 0 BrCl, your BrCl will act as products. So we're going to do plus 2x. Br2 and Cl2 will act as the reactants, minus x. Typically, the left act as the reactants, the right act as products. Not always, but mostly. And now for equilibrium, now we combine, right? Just like we did. Do the math. Well, now equilibrium is 1 minus x, 1 minus x, and 2x. So our equilibrium row now has x's in it. If you are solving for equilibrium concentrations, and all you're given is initial and a k, you're probably going to have x's. Now, let's write our K expression. Right, and I'm going to write it up here. All right, write our Kp expression. Kp, dealing in pressures, products over reactants. Pressure of BrCl squared over the pressure of Br2 times the pressure of Cl2. Well, remember, this is an equilibrium constant expression. We can use our K expression and we can plug all the values in. We know Kp. So the difference between what we did before and what we're doing now is before we were solving for K. Now we're using K to solve for equilibrium concentrations. So Kp is 1 times 10 to the negative fifth. Pressure of BrCl at equilibrium is 2x. That whole thing is squared. Br2 is 1 minus x times Cl2, which is 1 minus x. Now you might look at this and you're like, oh no, that's quadratic. But actually it's not. Because what I can do, 1 times 10 to the negative fifth is the quantity 2x squared. 1 minus x times 1 minus x is 1 minus x squared. These are both perfect squares. Now, if you really want to use the quadratic and multiply everything out, go for it. You're going to get the same answer if you just use perfect squares. So if I have the quantity 2x squared on the top and the quantity 1 minus x squared on the bottom, here's what I can do. Take the square root of both sides. When I take the square root of both sides, what's this? Square root of 1e negative 5 is 0.003162. Then it's 2 minus x over 1 minus x. I took the square root, so that got rid of both of the squares, and now it turns into algebra. So now it turns into, let's do an algebra problem. So my goal is to solve for x. I'm going to multiply both sides by 1 minus x. So then I get 0.003162 minus 0.003162 times x equals 2x. So 2 plus 0.003162. Oh, well, jeez. I'm going to move this just up here. 0.003162. So this is how it's just algebra. So what I did, I multiplied both sides by 1 minus x, and then I distributed the 0.003162. This arrow is just showing that my math is moving. This arrow is not like a mathematical function. I'm just showing you that I'm moving my work up here. So then to get here, I combined like terms. And then 0.003162, I'm going to solve for x, divided by 2.0036162. And x is 0.00158. There's x. So x lets us find the equilibrium concentrations. So the point of doing ice tables with x is to use the equilibrium constant to solve for equilibrium amounts. Now x is not any equilibrium amount. Once we have x, we need to make sure that we're plugging x into the equilibrium. So 1 minus 0.00158, 0.998, so 0.998, and 2 times 0.00158, 0.00316. So all of these are pressures, so these are ATM. But there are actual equilibrium concentrations. Notice how the pressure of Br2 and Cl2 is much greater than the pressure of BrCl. So this is looking at those ice tables, using X with ice tables. There are some questions like this in mastering. There are some questions like this in the practice that we'll look at today. Any questions on how we solved for this?
Oh, you're okay.
And if you need to go back and refer to this at any point, I am recording, so you can go back to the practice playlist and review these if needed as well. So the next thing that we're going to look at is Q versus K. So now we'll get back into looking at Q, looking at K. All of these pictures are right out of the notes. So again, I just copied, put into a slide from the notes, so that we can talk about why Q versus K. What's the importance of Q versus K? Why should we do any calculations? And then we'll actually solve for Q. So with Q versus K, this is the graphic that I like the most because it shows the arrow of the reaction that will be proceeding. And I'll talk more about this in a second. So Q is called the reaction quotient. Q can be QC or QP, just like K. It's calculated the exact same way. But Q is calculated with values that are at any point in a reaction. If you don't know if it's at equilibrium, you're calculating Q. It's at equilibrium when Q equals K. If Q is not equal to K, the reaction has to proceed in a certain direction to get Q equal to K. So Q tells us if a reaction is really at equilibrium, but it's looking at the current conditions. So nature wants Q versus K. All right, so nature wants Q versus K. But we don't always get Q versus K. So both of these graphics show how the reaction will proceed in order to get Q equal to K. So when Q is less than K, this is what we looked at in the do now. If Q is less than K, we need to get Q up equal to K. So the reactants are going to form more products. If Q is too great, we need Q to get back down. Notice how K is the same in every situation. K is a constant. This is why I like this graphic. And as we go through examples next week, or the do now next week, I will also be drawing this. I always draw this over on the side and use this to help. Because again, notice how K is the same size. K is a constant. If Q is less than K, this arrow is pointing in the direction that the reaction is going to proceed. It's going to go from reactants to products. It's going to form more products. That's going to make your numerator greater, and that's going to get Q equal to K. If Q is too great, well, then you're going to have products forming more reactants. You need to use up some of the products and create more reactants to get that fraction to equal. I really like this picture to help visualize Q versus K. It's hard for me to think about a fraction all the time, so I like this because I can visualize which way the reaction has to proceed to get Q and K equal. So K is a constant, Q is not. Right? K is the equilibrium constant. Q is just a quotient, right? Are we at equilibrium or not? Right? Just dividing. So now we'll look at some examples. So we're going to switch now to example 15. So example 15 is on page 14. If you want to make yourself a note, example 15 is like number 19 on mastering. It even uses the same substances. Right? So number 15 is like number 19 on mastering. And if we read this example, at 100 degrees Celsius, the equilibrium constant for this reaction has the value of 2.19 times 10 to the negative 10. So they gave me a value of K. Underline, circle, something. Right, this is important. As long as we're at 100 degrees Celsius, this is the equilibrium constant. So then it says that the following mixtures of CoCl2, CO, and Cl2 at equilibrium. When it's asking, are they at equilibrium? That should immediately tell you Q versus K. Are they at equilibrium should immediately tell you, are we at, or where does Q compare to K? So if we take a look at part A. Now before I do anything, I'm going to go ahead and up here, I'm going to write, so it's Kc. I'm going to write the Kc expression up here. Products over reactants. Because they tell us that we have concentrations, we're assuming these are aqueous solutions. Concentration of CoCl times concentration of Cl2 over concentration of CoCl2. There's my Kc expression. The reason that I wrote the Kc expression is because QC is calculated the same way. QC is calculated the exact same way as K. So we're calculating Q because it's asking, are they at equilibrium? The reaction quotient is a variable that can be at any point in the reaction. So CO times Cl2 over CoCl2. Just like K, Q does not have units, so you don't even have to worry about putting units into the expression. So 3.3 e to the negative 6 times 6.62 e negative 6, and I'm going to divide that by 2 e negative 3. 1.09 times 10 to the negative 8. There's Q. Now, when you get into scientific notation like this, sometimes it can be hard to tell which one is larger, which one is smaller. So I always suggest starting with looking at the exponent. Negative 8 compared to negative 10. So then think which one is greater. Negative 8 or negative 10? Well, negative 8 is actually a greater number. There are less zeros when it's times 10 to the negative 8. So now I'm going to compare Q to K. Negative 8 is a larger number than negative 10, so Q is greater than K. Now I'll draw this little picture over here, right, that we just had on the board. Here's Q versus K. Here's Q versus K. And Q versus K. So the reason I'm drawing this off to the side is so that it helps us look at which way the reaction has to proceed. Well, here Q is greater than K, so we're looking at this scenario. Q is too big. K cannot change. Q has to change. So when Q is greater than K, Q needs to decrease. This arrow helps me to say which way the reaction has to proceed. Well, if the arrow is pointing this way, products are going to create more reactants. So what we'll say is that the reaction proceeds to create more reactants. And actually, if we think about which reaction is proceeding, if it's products creating reactants, we can actually say the reverse reaction. Reverse reaction is products going to reactants. That's when Q is greater than K. So what I want you guys to do just really quick is calculate B and C. Just calculate. We'll focus on the Q versus K part, but I want you to calculate QC for parts B and for part C. So calculate QC using the information that they give you. So in B and C, you're just calculating QC. Again, it's calculated the same way as KC, but it's Q because we don't know if we're at equilibrium. So for part B, when you calculate QC, you should get 5.5 times 10 to the negative 12. Well, compare Q to K. Always compare Q to K to tell where you're at related to equilibrium. Look at the exponent, negative 12 compared to negative 10. Negative 12 means there's 2 extra zeros, makes it a smaller number. So here, Q is less than K. Now we're in this top scenario. When Q is less than K, we need to increase Q to get to equilibrium. Well, to increase Q, this is why I like these diagrams so much. This is showing the arrow of the reaction that's going to proceed. Reactants will proceed to produce products. So if reactants are forming more products, that's the forward reaction. So we'll say forward reaction, that's reaction, proceeds to create more products. Because when it creates more products, that's going to increase the number on the top, decrease the number on the bottom, and that's going to get us closer to Q equals K. Now in the case of part C, when you solve for part C, you get 2.19 times 10 to the negative 10. Well, compare Q to K. Q is 2.19 times 10 to the negative 10. K is 2.19 times 10 to the negative 10. Q equals K. When Q equals K, there's no need for a reaction to proceed because the reaction is at equilibrium. So if we don't know if something is at equilibrium, we're calculating Q. And then we compare to our equilibrium constant, K, to figure out which reaction must proceed, the forward or the reverse reaction. What do we have to create more of? So I'm going to have you guys actually try example 16. So example 16 says calculate QP for each given set of conditions and then determine in which direction the reaction will proceed in order to reach equilibrium. So now it's QP. You just have this table. The table is just a way to help you organize all of your information. The only thing I would suggest, now if you don't show all of your work here, I mean, it's your notes. But I would suggest, again, practice writing the Q expression. Right, here's your KP value. Write the expression first. So KP, right, or QP, either one. But just write the expression first to make sure you have your exponents. Products over reactants. So P, we're dealing in pressure. Pressure of SO2 squared times the pressure of O2 over the pressure of SO3 squared. Now that you have that, that's going to help you as you're plugging everything in. So take just a couple minutes. Here's SO3, SO2, and O2. These are 3 different scenarios. So calculate Q for reaction 1, reaction 2, reaction 3, and then in which direction will it proceed. So you can say that forward reaction will proceed. That means that reactants are forming products. You can say reverse reaction will proceed. And that means that products will produce reactants. So take a couple minutes, plug in your values, compare Q to K. I'll do one kind of example calculation. And using your exponents. So once you calculate Q, you want to compare Q to K. So make sure you're comparing Q to K to see which way reaction will shift. So K is up here, 0.338. So I like starting my reasonings with either Q is greater than K, less than K, or equal to K. So in the first scenario, Q is greater than K. So when Q is greater than K, we need to make more reactants. So we'll say reverse reaction will proceed to make more reactants. So when Q is greater than K, we need to decrease the value of Q. And so to decrease the value of Q, we need less in the numerator, more in the denominator. So we'd say the reverse reaction will proceed. Right? Or when it says toward the left or toward the right, that means we would actually say it would proceed to the left. The arrow points to the left. That's this toward the left or toward the right. You can think about which way will the arrow point. Will the arrow point to the left? Will the arrow point to the right? It's just these arrows right here. This arrow points to the left. It's going from products to make more reactants. Q is less than K. Right here, we would say the forward reaction will proceed. Right, we need to make more products. To make products. Or we can say it will proceed toward the right. So if we want to make more products, the arrow is going to look like this. And then in the third one, Q equals K, we're at equilibrium. It's not going to proceed in either direction. So again, that's looking at Q versus K. Which way will the reaction proceed? So Q versus K, we'll talk more about on Monday when we talk about Le Chatelier's principle. All right, so for these examples, yes, your packet, they all look the same color. In my packet, they're also all the same color because my packet is your packet. However, I just used a pen, especially this first one. The other two, if they're different colors, it's not a huge deal. But this one, they all look the exact same in the packet. So you can always just go off of what's on the screen. If you want to color them in, you can. Like, I just used colored pens and colored two of them in, or highlighters or anything. Just remember, you can always go back. These are in the Do Now slide, so if you want to go back and look at these, you can as well. So, for example 23, all these particle diagram questions are on page 17. This question just asks, are each of the following at equilibrium? That's it. Are they at equilibrium? So they give us this at equilibrium particle diagram. Right? They give us the at equilibrium particle diagram. And so to add up here, if we didn't want to know if we're at equilibrium, that is Q versus K. Are we at equilibrium? That's looking at Q versus K. So we need to know what K is. Well, here's equilibrium. here's the particle diagram for equilibrium. So this will allow us to solve for K. Now, whether it's Kc or Kp doesn't matter. I'm going to use Kc. I'm just going to assume that each of these particles represents 1 mole. So I'll write the assumption that I'm making here. Assume each particle equals 1 mole. So then I can just count. The biggest thing with particle diagrams is just counting. Count your number of particles. So this one is already at equilibrium because it tells me at equilibrium. So I'm going to write my Kc expression up here, just the expression, and then I'll plug things in down here just to save some space. So Kc is products over reactants. So the product of Z, or concentration of Z over the concentration of Q, nope, that should be Y, times the concentration of Y squared. There's my Kc expression. Again, we're assuming that all of these are aqueous because we're assuming this is 1 mole inside a container. They're all the same size container, so I'm just going to say 1 mole, or I guess we could even say 1 molar or 1 atm. And then the biggest thing with particle diagrams is just counting. Count your number of particles. So for K, when I want to solve for K, and the reason that I'm solving for the equilibrium constant is because I know this particle diagram is at equilibrium. Tells me. So I need Z on the top. I'm going to count all of my Z particles. If you look at the screen, those are all of the blue particles. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I have 12 particles of Z. Q is yellow. I have 3 particles of yellow. I have 1 red, 1 Y. Remember, Y should be squared. So to calculate K, 12 divided by 3 times 1 squared, so 12 divided by 3. Kc is 4. The reason I needed to calculate K is because if I want to know if vessel A, B, and C are at equilibrium, I need to compare Q to K. Now we have our value of K. Now we can calculate Q. So for each of these, we'll calculate Q. Okay, so for vessel A, we're counting all of our particles, so it's Z over Q times Y squared. Z, 1, 2, 3, 4, 14 over, Q is the yellow, 1, 2, 3, times Y squared. So then you're calculating Q, 14 divided by the quantity 3 times 2 squared. So what is that, 14 divided by 12? Q is 1.17. Is vessel A at equilibrium? No. No. Q does not equal K. So under here I can actually say Q is less than K. We're just reviewing the Q versus K thing again. Q is less than K. We actually need more product. Is it asking us to talk about what we need more of? No, but just to review. Vessel B. Calculate Q. So 16 particles of Z. 1, 2, 3, 4 particles of Y. 1 4 Q's and 1 Y. Y is squared. So 16 divided by 4 is 4. Are we at equilibrium? Yeah. Q equals K. This one's at equilibrium. And then if we do the same thing for vessel C, over 1Q times 2Y squared. So 20 divided by 4 is 5. Is vessel C at equilibrium? No. And in this case, Q is greater than K. So when Q is greater than K, we need more reactant. So when you're looking at particle diagrams, it's still applying the same concepts. At equilibrium, if you want to know if something is at equilibrium, that's Q versus K. Particle diagrams are about counting the number of particles. Count the number of particles, plug it in to your Q expression or your K expression.
K always stays the same, and if it isn't,
Yes. So at equilibrium, the value of K is always the same. So if you're at equilibrium, K is 4. If you're not at equilibrium, you're no longer calculating K. Notice how in vessel A, B, and C, we didn't know if we were at equilibrium, so we were calculating Q. And then to see if we were at equilibrium, we compared it to our equilibrium constant. We compared it to K. So K is a constant. K never changes unless you change temperature. Q is what is changing. All right, so then example 24. So I want you to take a look at example 24. Take a look at example 24. See if you can tell what time the system reaches equilibrium. So this is actually going way back to how we tell if something is at equilibrium. So read through 24. See if you can tell what time the system reaches equilibrium. So you have 0 minutes, 10 minutes, 20 minutes, and 30 minutes. Counting your particles could be useful as well. So sometimes it might help to just count the particles underneath, or just count them, kind of right next to it. At what point, right, at what time does the system reach equilibrium? 20 minutes. So equilibrium was achieved at 20 minutes. Because after 20 minutes, concentrations are constant. Concentration remains constant. So the reaction keeps going, but concentration remains constant. Equilibrium, the definition of equilibrium is when the forward rate equals the reverse rate, and we see that occurring when the concentrations remain constant. Okay, so we're actually going to just do example 25 like as the do now on Monday, just to give some time for practicing today. So there are some pages in the practice packet. I would really suggest page 9 and 10 because it's practice with ice tables and X. So page 9 and 10 in the practice packet is practicing with ice tables and X, so calculating equilibrium concentration. A lot of these also